In this video, we're talking about the graphs of logarithmic functions. And we can get these graphs by first looking at the graphs of their exponential counterparts or their inverse functions, y equals b to the x. And we use what we know about inverse functions to do this. So y equals b to the x for b is greater than 1 looks like this. And this is really the same shape regardless of what b is. And then similarly for b being between 0 and 1, here's the general shape. And again, that's just a general shape. It's not an exact graph right now because we don't have a value for b, but they'll all have that same structure and shape. So next, when we talk about inverse functions, we are going to take the function, if we call this like f of x, for instance, and we reflect it over the line y equals x. And the reason is because we are switching the role of x and y when we create an inverse function. So we're going to do that by switching x and y over the line y equals x. So when we do that here's its mirror image. This is the graph of y is equal to log base b of x. And then this point here, 0, 1, gets mirrored directly across this line, and it, of course, switches the x and the y coordinates. And then similarly, if b is between 0 and 1, we're going to have this graph. This is y equals log base b of x. And again, you don't really have to include this second case because you can use what we know here and translations to get the graph of log base b of x when b is between 0 and 1 if you wanted to. But this sort of completes the set, I think. Makes it a little easier if we just have them both sort of in our toolkit. All right, so for both of these functions, they're going to have the same domain, and that will be 0 to infinity. And hopefully this makes sense because if we look at the range, we get negative infinity to infinity. But what we've done is we've taken the domain and range of y equals b to the x, and we've switched it to get the range and domain of y equals log base b of x. And again, that should make sense because to get a function and its inverse, we're going to switch the x and y. Because domain represents x's and range represent y, we are switching those from y equals b to the x to the graph of y equals log base b of x. All right, and similarly with, we had a horizontal asymptote for y equals b to the x. If we reflect that horizontal asymptote about y equals x, we're going to get this vertical line. And that is our vertical asymptote for both of these graphs. So we have a vertical asymptote for the log functions, whereas the exponential functions, we had a horizontal asymptote. And now both of our log functions are going to have an x-intercept that is 1, 0. And there's no y-intercept. And it's just like what we had with the exponential function. We had a y-intercept of 0, 1 and no x-intercept. So that's reversed now. Okay. And we can use these basic graphs and what we know about translations to get more graphs. For instance, like y equals log base 2 of x plus 1, or y equals log base 2 of x minus 3, or whatever it is. We can use the basic shapes of these graphs along with what we know about translations to get more functions graphs. All right, a couple things to be careful of here. Log base b is a function, so something has to go into it. And it's essentially saying it needs an input, just like square root. You don't just write a square root, you write something inside of that square root. So that means that if we had log base 3 of 27 over 27, we cannot just cancel that to get log base 3. That doesn't mean anything. It's just like if you canceled out something and your answer was square root. Like square root of what? It doesn't mean anything. So be careful of that. And then one other thing to be careful of, log base 3 of 9 over log base 3 of 3, we cannot just cancel the log base 3 and the log base 3 there because those are functions. Much like we can't cancel sine of 45 over sine of 10. We can't cancel the sign that way because those are functions. Okay, the actual answer here you could find by simplifying log base 3 of 27, that is 3. And so this whole thing on the left, this one would be 1/9. And then over here, we can find or evaluate what log base 3 of 9 is. That's 2. And then log base 3 of 3 would be 1. So this answer would be 2. So you can definitely see that this is not going to be the correct answer. All right, let's just go through a few examples now. So which is bigger, log base 2 of 3 or log base 3 of 2? And you have to be careful because most calculators, you can't plug these in because they only have log base 10 or log base e, which we'll talk about in a bit. But the way I do this is I rewrite each one of these as an exponential form. So I said that this is equal to x, log base 2 of 3 equals x, and I write it in exponential form. So x is going to be the number that I raised 2 to in order to get 3. And this has to be bigger than 1 because if I had, if this were equal to 2, then I'd have x equals 1. But because it's bigger than 2, this exponent must also be bigger than 1. Similarly, over here, I'm going to change this log base 3 of 2 to be equal to y, and then I'll change it to an exponential form, which is 3 to the y equals 2. So now I have 3 raised to some number, but it's smaller than 3. So that means that y must be smaller than 1. So we can decide, or we can now tell that log base 2 of 3 is bigger than log base 3 of 2. And again, most calculators can't do those calculations, the log base 2 of 3 or log base 3 of 2. All right, so now we're going to evaluate these. So it means we're trying to find a number answer. Okay, so I'm going to call this x, and that way I can switch it to exponential form, which I feel a little more comfortable with. And it at least gets me somewhere to go. Sometimes I don't know what I need to do with logs. And if you're ever stuck like that, it's often a good idea to change forms. So here, if I set this equal to x, I'm going to change the form. So I get 2 to the x is equal to 8 root 2. I want to change these to be the same base. So 8 is equivalent to 2 cubed, and square root of 2 is equivalent to 2 to the 1/2. I can combine this by adding the exponents. Those are some exponent properties or rules we talked about before. So now I have 2 to the x is equal to 2 to the 3.5, which means that x is 3.5. And then I have the similar idea here. I'm going to change this to like an equation to solve. So I'm setting log base 16 of 1/4 equal to x, and I'll change that to exponential form, which would be which would be 16 to the x is equal to 1/4. So these, I can make both of them base 4. So 16, that would be 4 squared. And then 1/4 is 4 to the -1. And we've solved equations that have the same base in a previous video, if you need to go back and review that. All right, so now that I have the same base, I can set the exponents equal to each other. So I have 2x is equal to -1. So x is equal to a -1/2. All right, last one here, I promise. Give the domain of the function or equation y is equal to log base 3 of 10 minus 5x. So we're not actually graphing it, we're just finding the domain. But because we talked about the domain of the log function earlier, we said that sorry, I'm going to scroll up. We said that the domain of the basic log function is 0 to infinity. What that means is that the input here needs to be positive. So since we know that the domain of y equals log base b of x is all x where x is greater than 0, I'm just going to take the function I have and the input and set it greater than 0. So now I'm solving this 10 minus 5x is greater than 0. And again, I'm just taking the input of the log function here and greater than 0. The base here really doesn't make a difference to our answer. The input will need to be the same either way, and the domain is going to be the same regardless of what this base is here. All right, and so this is an inequality we know how to solve. I get x is less than 2, or 2 is greater than x is another way to phrase that. And in interval notation, I have -∞ to 2. Okay,